Okay, thank you very much. Thank you very much, Srinivas, for this introduction. Hello, everybody. I'm very pleased to be with you today. So my name is Diego, and obviously the topic of today will be Actran. So more specifically, the agenda I have prepared is that first I will introduce the content of the Actran software. Then we will focus on how to solve an acoustic radiation problem with Actran. We will review the baseline assumption for such analysis, which is called a weakly coupled vibro-acoustic analysis. Then we will look at the different steps of the computational process and the key ingredients of the related Actran model. We will also review an example of application that is the radiation of a gearbox. I will then guide you through Actran VI, the graphical interface of Actran during a live demo. And finally, I will conclude in one slide, and then we're going to have the Q&A session. So the Actran software is divided in different modules according to the different features that are available. And first, we start at the bottom with the acoustic module, which is really the core of Actran. So this module contains everything required to solve pure acoustic problems. So there are acoustic finite elements, acoustic infinite elements, acoustic excitation. All our algebraic solvers are there. And we also have the ability to account for complex phenomena like flows, temperature gradients, or to include any kind of acoustic absorption. Then, if we increase the complexity of the problem by combining the acoustic physics with structural dynamics, we end up solving a fully coupled vibro-acoustic problem, and that's the purpose of the vibro-acoustic module. So this module includes structural finite elements like viscoelastic and composite shells, solids, beams, poroelastic elements, and all the necessary boundary conditions. And if you go one step further in the complexity, and if you want to solve, for instance, a full trim body analysis using Nastran to represent the body and Actran to represent the trim components, then you need to use the Actran for Nastran module. And if you combine the acoustic physics with aerodynamics, then you start looking at aero-acoustic problems. And that's the purpose of the Actran aero-acoustics, a module that is used to compute the aero-acoustic sources from unsteady CFD results and then predict their acoustic radiation. And then after, we also have two other modules that are targeted for aircraft turbofan engine noise, but I'm not going to talk about that today. So it's important for you to remember that all these modules can be combined with each other. So it's, for instance, perfectly possible to solve a fully coupled aero-vibro-acoustic problem by combining the features of the vibro-acoustic module and the aero-acoustic module. And all these different modules are integrated in Actran VI, the dedicated pre- and post-processing tool of Actran. So the topic of today being the acoustic radiation analysis, we will focus on the acoustic module. The other modules will be covered by other webinars that will be organized in the coming months. So Actran is based on the finite element method that is complemented by infinite elements to account for the radiation in free field. Actran can really be seen as a multiple ball toolbox, and different computational sequences are available to solve your acoustic problem. First, there is a direct frequency response that is the most popular sequence. The solution is computed in the so-called physical space, and the model can include any kind of complexity or damping mechanism. There is also the modal frequency response, where the solution is computed using a preliminary reduction in the modal space. So this is very well suited for interior vibro-acoustic problems, and modes extracted by Nastran, for instance, can be used. Then we have the hybrid modal physical approach, which basically combines the best of both worlds. And in such analysis, the structure is usually represented in terms of modes, and the acoustic field is solved in physical coordinates. Then we also have a modal extraction solver to compute the modes of undamped structures or undamped cavities. We also have more advanced sequences like a time domain solver or a comprehensible flow solver. So Actran is compiled on Linux and Windows platform, both in 32-bit and 64-bit versions. We have very efficient solvers available to solve the algebraic problem. We have direct solvers, we have iterative solvers. All of these solvers include a multiple load case capability, meaning that different excitation can be solved independently, but all at the same time for almost no extra cost. Then finally, we have different types of parallelism that are available, so the computation can be spread on different processors according to different strategies that are available. So we have frequency parallelism, domain parallelism, or matrix parallelism. So the Actran acoustic module is based on acoustic finite elements and acoustic infinite elements. So if you look at the above figure on the right-hand side, you can see that infinite elements are always combined with acoustic finite elements. So acoustic finite elements will be used to model the propagation in the near field of the source, and then acoustic infinite element will be used to model the radiation in the far field. And because Actran uses finite elements, we can account for complex phenomena, like for instance, viscothermal losses occurring in narrow channels, or we can account for the effect of the flow or of temperature gradients on the acoustic propagation. So Actran includes a wide range of acoustic excitation, but the vibration levels can also be imported from MSC Nastran or other structural FEA solvers. And that's really a key ingredient for solving the acoustic radiation problem. The typical information that will be computed by Actran is, for instance, the acoustic pressure or the acoustic intensity at any point of the system, or Actran will compute the global radiated power by the source. And based on that information, we can also access, for instance, the power repartition or compute the radiation efficiency. The typical application examples are the acoustic propagation in intake or exhaust lines, or the acoustic radiation from vibrating structures like a car engine or a gearbox. And all these features can be complemented by other features like vibro-acoustic or aero-acoustic features to solve more advanced problems. So a few words about the infinite elements. So the infinite elements are the natural extension of acoustic finite elements to model the far field radiation. So you cannot see these infinite elements, you can only see their footprint on the finite element domain. But these infinite elements are actually finite elements in the sense that they have higher order shift function that are used in the radial direction. And the purpose of this higher order shift function is to first act as a non-reflective boundary condition, meaning that an acoustic wave that goes in that direction cannot come back in the other direction. And then it's also used to compute the pressure fields far away from the source. So a problem that is a vibro-acoustic problem, it's basically a problem where the vibration of a structure will induce a pressure fluctuation, and the pressure fluctuation will also induce vibration in the structure. So when we look at the fully coupled problem, it means that we take into account all these different interactions that occur at the same time. And when we do that, we speak about a two-way coupling or a strong coupling. But in many circumstances, we can actually neglect the retroaction or the feedback of one element on the other. And in that case, we speak about a one-way coupling or a weak coupling. And this is, for instance, the case when we consider a heavy and rigid structure that is radiating in a light and open acoustic medium like the air. And when we can do such a one-way coupling assumption, there is obviously a strong gain made on the computational time, because the structural and the acoustic problem can be solved separately. So existing structural models and existing results can be reused, and if you look at the acoustic computation, you will only have acoustic degrees of freedom, meaning that it will lead to a lower CPU and RAM requirements. So the weak coupling assumption is, for instance, not valid when we look at the radiation in heavy fluids, or if you look at interior vibro-acoustic problems. So in such cases, you need to do the computation in a fully coupled way. So when dealing with weakly coupled vibro-acoustic problem, the computational process is always divided in two steps. The first step of the process is the structural finite element analysis, and this step is usually performed in MSC Nastran. So the results of this step will be the vibration levels and the structural mesh that are stored in a dedicated file. And the second step will be the Actran computation, where both files will be used. And the results of Actran typically include frequency response function, for instance, frequency response function of the sound pressure level, or frequency response function of the radiated power. But you will also have access to maps at different frequencies of the acoustic field, or you will be able to look at waterfall diagrams. So in this presentation, we will focus only on the acoustic part of the computational process. So the transfer of information between Nastran and Actran is drawn through an acoustic boundary condition that is created from the vibration levels computed by Nastran. And because the Nastran mesh usually has a different mesh refinement than the acoustic mesh, then a mapping strategy will be required. And these two ingredients are embedded in Actran in what we call the BC mesh feature, and BC mesh stands for boundary condition mesh. So because we use finite elements to model the acoustic medium in the near field, a 3D finite element mesh is required prior the analysis. And so the element size must be small enough to capture the smallest acoustic wavelength and the small fluctuation very close to the structure. So typically in Actran, we will use only 4 linear elements per wavelength, and this is possible thanks to optimized integration rules that we have implemented in Actran. So the meshing process is easy and is always similar. First, you will need to create a closed surface around the structure, and this surface will be used to project the vibration results, and this surface is called the BC mesh surface. Then you will create another surface mesh at some distance from the structure, and this surface will support the definition of the infinite elements, and that's what we call the infinite element surface. And then the last step will be to create the 3D elements in between by doing some automatic 3D tape mesh in between. So Actran obviously supports the Nastran format to import vibration levels, but that's not the only format we support. And the table here gives you the other possibilities that we can use. So the vibration levels can be either acceleration, velocities, or displacement, and these quantities can be expressed in physical coordinates, but can also be expressed in terms of mode shapes and participation factors. And the different subcases present in the Nastran analysis will be treated independently, but simultaneously and automatically thanks to the multiple load case capability. Therefore, the solution will be available for the different RPMs at the end of the computation. So Actran automatically computes global quantities like mean sound pressure levels or global radiated power, but can also give you access to local indicators anywhere you want. So for that purpose, you need to define what we call virtual microphones or field points, and these virtual microphones can be defined anywhere inside or outside the finite element domain, thanks to the use of these infinite elements. Then you also have maps of the acoustic fields that are available on the acoustic mesh, or you can define post-processing mesh, and that's something we call in Actran a field mesh. So the global radiated power by the system can be computed on any surface, but can also be computed according to the ISO standard automatically. This is something very useful to compare Actran with standard test results, for instance. Then we also have waterfall diagrams. So a waterfall diagram is a 2D color map where the response, for instance, the sound pressure level, will be computed versus the frequency and versus the engine order. So such diagram can be obtained automatically after one single Actran computation thanks to this multiple load case capability. And looking at such diagram, you will be able to identify some phenomena that are system dependent, like for instance structure modes, and this will be typically vertical lines on the waterfall diagrams. But you will also be able to identify phenomena that are excitation dependent, and typically that will be diagonal lines on the waterfall diagram. So now we're going to look at a short application review, that is the radiation of a gearbox. So for that case, the vibration levels have been first computed with MSC Nastran. Then 2 acoustic models have been built in order to compare the radiation of the gearbox in free field and the radiation of the exact same gearbox in half free field. So the goal of the simulation is actually to assess the effect of the floor on the sound pressure level computed at different locations. So in the model, we have placed different virtual microphones at different locations around the engine. So the frequency response of the sound pressure level is computed for these different microphones with floor and without the floor. And this is plotted in this slide, and you can clearly see that basically the impact of the floor will depend on the position of the microphone. And this is confirmed by looking at pressure maps that are given here for 3 kHz. So if you look at the pressure maps with floor and the pressure maps without floor, you can also then compute the map of the delta of the pressure levels. And using these delta maps, it's very easy to identify what are the locations where the impact of the floor will be the most significant. Okay, now what I propose is to guide you through the graphical interface during a live demo. So in this demo, we will again look at the radiation of a gearbox. So the vibration level has been computed with Nastran, and what I will show you, I will first show you how to set up an Actran model based on an existing finite element mesh, and then we will do the post-processing of the acoustic results. Okay, so this is a view of our graphical interface, so Actran VI. And so the main window of Actran VI is actually divided in 3 sub-windows. On the right-hand side, on the top right-hand side, you have what we call the render window. So that's where basically you will be able to visualize the model. Then on the left-hand side, we have what we call the data tree panel, which is basically a tree visualization of the Actran model and all the ingredients you have in your analysis. And then on the bottom, we have what we call the toolbox, which contains different features that are very useful to create some elements you will need in your analysis, or also to create some post-processing results or operations. And so during this demo, we will basically travel from and use all these 3 ingredients. So the very first operation is always to import the mesh, and you can see that we support many different formats. So for instance, we support the BDF format, but for the purpose of this demo, we will import a mesh in the Actran format. Here we go. So first, I will look and identify the different zone of my mesh. So first, I change the color. Then the first thing I can identify is this BC mesh surface that will be used to project the vibration levels. Then I have my infinite element surface that is located at some distance from this first surface. And then in the middle, I have my 3D finite element mesh that will support my 3D finite element, my 3D acoustic finite elements. So then the first step is to create a material to support the analysis. So I need to define a material, and for that I will basically import a material that is available in our database. And because the model has been created, has been computed in Nastran in ton and millimeters, I will select a material expressed in ton and millimeters. And you see, if I double click here, I have the list of all the properties that will be used, and the two major ones that are needed actually is the sound speed and the fluid density. Then the next step is to create the analysis. So for that, I right click on the analysis branch, I select a direct frequency response, and you see here on the left hand side, I have now a tree that has expanded, and I have here the different ingredients that I will need to fill to create my Actran analysis. And so to create this analysis, I have two ways. I can either go here and create and fill the different spots of my tree, but I can also use a shortcut of my property window, and that's what I'm going to use mainly. So the first step I'm going to do, I'm going to create a finite fluid component. And so my finite fluid component needs to refer to my acoustic medium. And then I need to apply this acoustic medium to one of the domain of my mesh, which is my finite element domain here. That's it. So I do exactly the same for the infinite fluid component. So I will select the acoustic material. I will apply it on my infinite element surface. But here I need also to set up few numerical parameters, like the interpolation order, which is the order of the shape function used by the infinite elements. So I will here use an order 10. And then I also need to set up a reference coordinate system. And for that, I need to put the center in the center of my model, which is in that case 0, 0, 0. And then I need to define three axes, and I will use the three axes that have a 1 meter dimension. So because I'm working in millimeters, I need to multiply everything by 1000. And I can visualize my coordinate system, and I will show you that. So I can see here that it's perfectly well defined. It's well centered in my finite element domain. So I will remove the visualization, and I'm done with the infinite element definition. So next step I need to do, I need to create my coupling surface where I will project the Nastran results. So that's done like this here. And I simply apply my coupling surface on my BC mesh surface. Here we go. Then I need to create the boundary condition, meaning I need to tell to Actran what are the files, what are the Nastran files that will be used, what are the type of quantities I'm going to import, and that's done using this BC mesh boundary condition. So I need to select the format of the mesh, which is Nastran BDF. Then I go and I pick the BDF file. Then I'm going to select Nastran OP2 format. And I need to pick the right OP2 file. Then my type of results are displacement, and I want to apply that on my coupling surface. Here we go. So when we have done that, we have done 70% of the job. Then I need to tell to Actran that it needs to use all the load cases that are available in the Nastran OP2. So I need to trigger the multiple load capability. I also need to specify the frequencies, and for that I want to pick the frequencies that are available in the Nastran OP2 file. So I select here get frequencies, Nastran OP2, and again I will point to the OP2 file. I need to define a solver. I want to use the months solver. And when I have done that, I'm almost done, except that I didn't do one very important thing. I did not specify the output quantities I want. And in that case, I want to look at the directivity of my gearbox. So I want to define an arc of microphones where I will look at the sound pressure level. So for that, I go here in the toolbox, mesh creation, fill points. So these fill points are the virtual microphones, and I will create a circle of microphones around my gearbox. So I need to enter the start angle. I want to have 361 microphones. I want it to be on the 1 meter sphere. Here we go. And you see now that I have a very nice arc of microphones. I want also to look at maps of the pressure field. And so for that, I will create this post-processing mesh. And I can again use the toolbox for that. So I will create a Cartesian grid that will be a 2 by 2 meter grid. Oops. I don't want to have anything in the Z direction. I want to have 40 elements in all the directions, and I want to create a field map. So you see here, now I have this Cartesian grid that will be the post-processing mesh. So when this is done, the only thing I still need to do is to tell to Actran what are the names of the files I want to output. So I want my FRF files to be with this name, and I want my field map to first be in the native Actran format, and I want this to have this name. I want to have the frequencies, I want to have all the frequencies output, and that's it. So when this is done, I'm finished with the pre-processing. So I can run the computation. So for that, I can go here. I simply drag and drop the analysis. And then I can launch the computation. So to save time, we will now post-process the results on computation that I've already run on my computer earlier today. So the first thing we are going to look at is the frequency response function. So for any of the microphones I have defined, I can basically plot the sound pressure level versus the frequency for the different load case, for instance. So for instance, here I look at one microphone and I put the different load case. Because my model is in millimeters, I need simply to adapt the dB value, so I need to add 60 dB. Oops. That's just to have the correct dB value. So by doing that, I have the sound pressure level for different microphones versus the frequency. But what I want to look at is the directivity. So I don't want to have one microphone. I don't want to have all the frequencies for one microphone, but I want for different frequencies to have all the microphones on my figure. And for that, we use what we call in Actran a reverse set. And when we do that, we plot for one frequencies all the microphones. Here we go. And then I use a polar plot, and I have now a very nice polar diagrams, and I can plot for this frequency all the different load cases, and I can see that indeed my load cases have a strong impact of the shape of my directivity. So I can see, I can maybe look at an higher frequency to see if it changed something. And obviously it changed a lot. You can see that the directivity pattern is much more complex, and that's pretty much what we were expecting. So to see if this is confirmed, I can also look at maps of the response. So to do that, I go here, and I want to have the map in dB. And you see here, I have the map in dB for the first frequency of computation, but I can look at 400 Hertz. And indeed, if I change the excitation ID, I see that I change very much the pattern of the sound field. And if I even go to a higher frequency, I indeed see that the pattern becomes much more complex, and it's still very dependent on the excitation. Okay, so I think that's done. That's it for the demo. So I think it's now time to conclude the presentation. So you have been introduced during this presentation to the main features of Actran for acoustic radiation. So we have reviewed the computational strategy that is based on a weakly coupled approach, and it's a two-step procedure. So the first step is the computation of the structural dynamics using MSC Nastran, and then the second step is the radiation, the computation of the acoustic radiation done in Actran based on MSC Nastran results computed in the first step. And if you think the process that way, you can really consider that basically obtaining the radiated noise by a structure is nothing more than a post-processing of MSC Nastran results using Actran. So we have also, during a demo, we saw that the pre- and post-processing operations are straightforward in the graphical interface. And if now we want to think one step further in analyzing this kind of model, we can increase the complexity, for instance, by accounting for the absorption or the shielding effects from covers. And that can be done by including features from the vibro-acoustic module. So that's it for the presentation. I thank you very much for your attention, and I will be happy to answer the question you might have.
Thank you very much, Diego.